Okay, we're live. So we're going to be talking about building volume by cross-sections today. So that means we'll be stacking a bunch of two-dimensional areas on top of each other in order to build three-dimensional shapes. So by finding the area of a cross-section and multiplying by how many cross-sections you want, we can end up building a 3D shape that has volume. Okay, so before I really jump into it, let me show you what this will look like. Okay, so here I've got a cylinder, really. If I wanted to find the volume of a cylinder, so let's say something like a stack of coins. That stack of coins would have a radius and a height. So what we could do is I could start to take the area of one coin and then multiply by how many coins I have to get an estimate for what my volume would be. So what's the height of one coin, multiply by how many coins I have, and then what's the area of the face of one coin. And that would get me all the way through. Okay, so it would look something like this. If I took one two-dimensional cross-section, so here's, if you were to cut this horizontally, then you would end up with a two-dimensional shape. That shape would be a circle, since we've got a series of coins here. The area of that circle would be pi r squared. To get a three-dimensional volume, I could then multiply that two-dimensional area, pi r squared, times h. So that's how much height that we have total for the shape. Any questions so far? Okay. I could also represent this as an integral. So if I wanted to represent this as an integral, I could say because our volume is really our area times height, I am integrating, I am adding all of the areas times their infinitely small portions of the height. So in this case, my change in height, or dh, times the area for that cross-section, plus the next change in height times the area of that cross-section, plus the next change in height times the area of that cross-section. If I sum them all up, I'll end up with the volumes. Because integration is really just repeated addition, that's going to allow us to get the volume of the entire shape. Okay, but if we want to step further with this, so let's say I've got a bell shape here that I want the volume of, where it's not a regular shape that we have a formula for. Then we can use the same process. So I'm going to split this up into a bunch of two-dimensional cross-sections, so infinitely small horizontal cuts. Each one of those cuts has an infinitely small change in height, but each one of those cuts could be represented as a circular cross-section. So that means each one of these infinitely small cross-sections has an area that I can multiply by this change in height to get a volume of that cut. And when you add all of the cuts together, you'll get the volume of the shape. Put another way, the volume of any shape is really just an area times height. If our shape changes as we go up, then we can just keep stacking area times height plus area times height plus area times height as we change, and we'll get the volume. Okay. So in our example from earlier, so this is the video that we're showing right now. I have a circle with a radius of 2, and I'm stacking a bunch of isosceles right triangles on top of each other that are perpendicular to the x-axis in order to make a three-dimensional shape. Okay, if I was going to work this out, it would look like this. So each one of these triangles perpendicular to the x-axis could be drawn on a graph like this. So here I've got a circle with a radius of 2. And then cross sections that are perpendicular to the x-axis. So that's forming a 90-degree angle with the x-axis. Are these right isosceles triangles? So these would pop out of the page. Like this. Okay, if I was going to take this sheet of paper and look at it from the side, then it would look like this. This is a side view. And this is a top-down view. From the side, I've got an isosceles right triangle, so that right means I've got a 90-degree angle, which is here. If this angle is 90 degrees, and that means if this is an isosceles triangle, that the two sides are equal, which means the two angles have to be equal. So if this is 90 degrees, then I have 90 more degrees to split between these two angles. So 90 divided by 2 is 45 degrees, which gives me my two angles here that will touch the page, 45 and 45. If I wanted to drop an altitude to get the height, that way I could get the area of this triangle, since the area of a triangle is base times height. Then that line would split this isosceles triangle in half. So this 90-degree angle here for the whole triangle would become a 45-degree angle for this half triangle. Okay, this distance here, from here to here, half the triangle, is whatever the y value is right now of our function. So we could set this up using Pythagorean theorem with this half of our triangle, saying that this must be our y value, and that if this is 45 degrees and this is 45 degrees, that this side length must be equal to this side length, so our height is also y. Alright, any questions so far?
No.
Okay, so the area is 1/2 BH then. Or I could say the area of each individual triangle is 1/2 of y times y. Or y squared over 2. Now, that area was only half of our triangle though. I got the area of this half of the triangle here in black, but did not get the area of the white part. So I'm going to multiply that by 2 to get the area of the entire triangle, which would give me the area total. I'm going to call this area of the cross section. Is equal to y squared. Okay, going to my top-down view here. I have an infinitely small change in x on this side for my cross-section. So in order to get the volume of this cross-section, I would have to multiply the area, which is this space here in yellow that I'm going to draw, the area of all of this yellow part, which is the triangle we just found. And then multiply by the depth, which would be dx, our change in x. Well, since our area is y squared, and our depth is dx, my volume then would be my area times depth, or y squared times dx. Okay, but I would want to keep multiplying these cross sections from a start point to an end point. So I want to keep adding all of these cross sections together from x equals my start point to x equals my end point. That way, just like our video, we'll be able to keep stacking more and more of these triangles together in order to get the total volume. So from a start point to an end point. So if I want to keep repeating this, keep adding all of the area times depths from start to end, then I would have to integrate this from my start point to my end point. Now if this is a circle with a radius of 2, that means my start point would be at x equals -2, and my end point would be at x equals 2. So I'm going to integrate from -2 to +2 of our area, y squared, times our depth, dx. Okay, so that leaves us with, we just need the equation then of the y value in terms of x, which we can get from the equation of a circle. Okay, so I've got here, but I think I'm going to rewrite really quick to just explain what's going on. So the equation of a circle is x squared plus y squared equals r squared. We were told that our radius is 2, therefore the equation of our circle is x squared plus y squared equals 2 squared, or x squared plus y squared equals 4. If I want to solve for y squared so that I can plug it into this volume equation, and then we'll be able to integrate because I'll have variables that are all x's. And I can solve for y squared using this equation. So y squared equals 4 minus x squared. Okay, then I'm going to substitute. So our volume is equal to the integral from -2 to 2 of 4 minus x squared in terms of x. Okay, we can then integrate that normally. So this would be, if I integrate 4, I'll get 4x. If I integrate x squared, so this will become a negative x cubed over 3. And we integrated from -2 to 2, so I can plug in our bounds. And this will become our upper bound, 4 times 2 minus 2 cubed over 3, minus 4 times -2, our lower bound, minus -2 cubed over 3. So I've got 4 by 2 is 8 minus -8, or 16. I guess I'll write this out. 8 minus 8/3 minus -8 plus 8/3. Since -2 cubed is -8, and a negative times a negative is a positive. Okay, we can then distribute. So this will be 8 minus 8/3 plus 8 minus 8/3. Or 16 minus 16/3. 16 is 48/3 minus 16/3. which is 32 thirds. Or if you wanted to reduce, write it as a decimal, I guess, this would be 10 and 2 thirds, or 10.6 repeating. Okay, volume is equal to this. So our volume is 32 over 3. If we kept stacking isosceles right triangles on top of each other, onto a base that was a circle with a radius of 2, we would end up with a total volume of 32 over 3 units. Any questions on what we did? That was a lot.
So is depth always dx?
For your homework this time around, it will be. However, later on, we could start stacking our cross sections differently. So if we had said our cross sections instead are perpendicular to the y-axis, which would look something like this. So this is the same problem. I've got the same base, only our isosceles right triangles, instead of being stacked horizontally, are being stacked vertically. Okay, now if I draw this out, okay, in yellow I've got the area of the cross sections, which is still a triangle. But here in pink, oh, I guess purple rather, this infinitely small depth of our cross section, so sort of like the depth of our sheet of paper, is now my change in y, not my change in x. So it really depends on your orientation. Although, again, for the homework for today, your depth is always going to be dx. That won't be the case always. So this is if we had cross sections that were perpendicular to the y-axis instead. And then my volume would end up being the integral from a starting y to an ending y of your area in terms of y. Okay, I'm going to try a couple more, I think.
Wait, Mr. Brennan?
Yes.
So, for our shapes, we'll only use isosceles triangles, or will we use any other ones, such as rectangles?
We'll use some other shapes. So.
Okay.
I don't really want to start with semicircles. Let's do this one. Okay, so I've got this base of a solid, which is enclosed by this semicircle and the x-axis. So here's my semicircle and the x-axis. So I'm looking at the area between them, which is here in blue. Base just means the bottom of a solid. So right now we're looking at it at this shape from the top down. This would be the if you slammed this shape onto your desk, this is what the imprint would look like. So this is the bottom of your solid. Cross sections perpendicular to the x-axis. That's at a 90-degree angle to the x-axis. Are rectangles, and their heights are double the side that is in the xy plane. Okay, so if I was going to draw that out, it would look like this. I've got a cross section, which is perpendicular to the x-axis. So perpendicular to the x-axis at a 90-degree angle to the x-axis, popping out of the page. With heights of each rectangle. That are double the side in the xy plane. I'm going to redraw this really quick. So something like this. I have, keep my color code the same as last time, I think. Here in purple would be the depth of our rectangle, which is an infinitely small change in x. Okay, in yellow, it was a little bit thicker than I wanted. In yellow on that face side, we've got the area that we'll need to multiply. Okay, so given that, we were told that we had heights twice that was inside of the xy plane. So the xy plane is my coordinate plane. Inside the coordinate plane, I have this line here. I'll go green. So this line here is inside the coordinate plane. It's on the page. I'm told that the height of this rectangle is twice that length. So first, do a darker green, but here in green, what is this height? What is this distance? It's inside the page. Anyone? 3 point something right now. Okay, if I had to give a variable for it though, what variable would you use to find it?
X?
So my x value would tell me this distance from here to here.
Oh. No, but I mean we could plug the current x value into the equation, which is square root of 49 minus x squared.
Okay,
Then we would get the y.
perfect. So that would give you the y value, which is what we really want. That y value, wherever we are right now, will tell us this side of the rectangle that is inside the xy plane. Okay, which you're right, we could get by plugging in whatever the x value is right now into the equation they gave us, 49 minus x squared for the semicircle. But if this side here in green is y, and we were told that the heights that are popping outside the page, quickly running out of colors, but heights that are popping outside the page are twice that length. Then what does this length have to be in black? 2y, perfect. So what's the area of the rectangle in yellow?
2y squared.
2y squared, perfect. So area of cross sections is 2y squared. Okay, and then if I want to make that a volume for this box, I would have to multiply that area, 2y squared, times the depth. What's our depth?
Dx.
Our depth is our change in x. Which is, in our case, infinitely small. So if I wanted to stack all of these together, I would end up integrating, which will add repeatedly, every possible cross-section. So that's every possible 2y squared times dx, from a start point to an end point. So here's what that would look like. Our volume total would be equal to the integral from my start point to end point, which I'll look at in a second, of the area of the cross sections times the depth of each cross section. Okay, what's my start point and what's my end point? When will this semicircle touch the x-axis? When is y equal to 0?
-7 and 7.
-7 and +7. Perfect. I guess I'll do orange. -7 and somewhere in there. +7. If you're not sure, I would have calculated the intersection point of these two curves, so that's the x-axis and the y-axis, by setting y equal to 0 and solving for x. So I can square both sides. 0 is 49 minus x squared. Throw the x squared over to the other side. X squared is 49, and then solve for x. X is positive or negative 7. Gives us our start point and end point. Okay, so now I'm just going to plug in our values. Our volume is equal to our area, which we said was 2y squared. So volume is equal to the integral from -7 to 7 of 2y squared dx. Okay, but I do have a problem because this is y squared and this is in terms of x. So I can't integrate until our function is in terms of x. So how can I rewrite this, 2y squared, so that our equation is in terms of x instead?
Use the
Use substitution.
equation.
Okay, I'm going to use the equation here in green. We know y is equal to square root 49 minus x squared. So I'm just going to substitute. Wherever I see a y, I'm going to replace it with square root 49 minus x squared. Volume is equal to the integral from -7 to 7 of 2 times the square root of 49 minus x squared squared in terms of x. Okay, so one more time, what we just did was I took our equation for y and I substituted. Okay, if I'm squaring this square root, then those will cancel, so this square will undo this square root. That leaves me with my volume is equal to the integral from -7 to 7 of, I could just pull out this 2 since that's a constant, or you can multiply it through, either way works. I think I'm going to pull it out for now, so this will be 2 times 49 minus x squared in terms of x. Okay, any questions on our setup?
Nope.
Okay, then our last step is to integrate. So this will be 2 times all of our integral from our upper bound to lower bound. So that's 49x minus x cubed over 3 from -7 to 7. Or 2 times all of 49 times 7 minus 7 cubed over 3 minus 49 by -7 minus -7 cubed over 3. So I don't actually know what -7 cubed is off the top of my head, but I can throw that in here. 7 cubed, 343. Okay, so that means I've got 2 times 343 minus 343 over 3 minus -343 plus 343 over 3. Okay, correcting a mistake here really quick. So if I want to combine these, I've got 343 plus 343 is 686. Negative 343 over 3 minus 343 over 3 is 2 times 343 over 3, or negative 686 over 3. In order to get a common denominator, I would put both of these over 3, so that's 3 times 686 over 3 minus 1 times 686 over 3 would give me 2 times 686 over 3. And if I multiply all of that out, 2 times 2 times 686 is 2744 over 3. I'm a little bit less concerned about the final integration than I am about the setup for the homework today. Do you guys feel like you can do this, or do you want me to go through one more shape?
One more shape.
One more shape, okay, cool. So we'll try one more. Dun, 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 dun. How about this one?
Mr. Brandon,
Yes.
can we try to solve questions like number 3, where there are 2 y values? Something. Oh, wait, never mind. Like in the homework, something like number 4.
Okay. I'm looking for one that still has a semicircle. If I don't see one, I'm just going to regenerate until I get one. Whew, I'm not very lucky. Equilateral triangles, squares. There we go, semicircles. Okay, so this has what you want with 2 y values and a shape we haven't done yet, is what I was trying to get. Alright. So probably last one for today. I've got The base of our solid is enclosed by y equals 4 and y equals x squared. So here I've got two lines in blue. The line y equals 4 and the function y equals x squared. So what this is telling me is the area that we want is enclosed by these two functions. So the area between y equals 4 and y equals x squared is the area we want, here shaded in blue. So this area between them is the bottom of our shape. Okay, and then cross sections that are perpendicular to the x-axis are semicircles, which is a new shape we haven't seen yet. So if I was going to draw that out, that would look like this. Cross sections perpendicular to the x-axis. That means I have to form a 90-degree angle with the x-axis like this. Are semicircles. So popping out of the page are half circle shapes, which would look like this. Okay, once again, we have an infinitely small side here in purple. Which would be our change in x. And we've got a two-dimensional area that we'll need to find, which is the area of this semicircle, which I am shading here in yellow. Okay, so area of the cross-section in yellow, the depth of the cross-section in purple, where the depth is dx. How would I get the area of this half circle?
Pi r squared divided.
Pi r squared over 2, okay? So that's 1/2 of pi r squared, which means I do need to figure out what the radius is. Okay, so my radius would be here. Radius. That radius would be equal to what's the total distance from the top function to the bottom function?
Four.
4 is my distance from the top function to the x-axis. So that would be this distance.
3.
Okay, 3 is what it is right now, but I want a general form because as I move along this curve for all of these semicircles that I want to draw, we'll have infinitely many semicircles, and no matter, depending on where you are between -2 and 2, our answer is going to be a little bit different, right? So I need a formula, not just a number.
We can use the formula of the parabola and just substitute the x value, I guess.
Okay, so you're getting the y value of the parabola.
Yeah.
Okay, so that would be y equals x squared. And then what do you do with that y value?
We get our height for triangle that we need.
Okay, I'm going to color code again, I think. So right now, let's do I have a red? Yeah. Okay, here in red, think I'm running out of RAM. There we go. Here in red is y equals x squared. So I'm going to have a y value here. That is a height of x squared. Okay, if I want the distance here in black, and we know this distance here in blue is y equals 4. Then how can we get the distance here in black?
Four minus x squared.
Right. Okay, so our total distance here in black, that is 4 minus x squared. So what would the radius be then? So right now you've told me the diameter of our semicircle, so that's from top to bottom, is 4 minus x squared. If the diameter is 4 minus x squared, then what would the radius be?
4 minus x squared over 2.
Perfect. Okay, I'm gonna write our general form really quick. I'm gonna call this one y1, and I'll call this one y2. So my radius was y1 minus y2 over 2. Okay, which gave us 4 minus x squared over 2. Okay, that's the hard part. Any questions on our radius? My picture's a little bit full. Do you guys understand what's going on?
Yeah.
Okay. So I've got an area and we've got our depth. What can we do to get our volume?
One and a half pi square times.
Okay, so our volume is the integral, so I'm going to keep stacking all of these two-dimensional cross sections on top of each other infinitely many times from -2 to 2, our start point to our end point. Of, you're right, 1/2 pi r squared. Times what?
dx.
Dx, perfect. And that will make us three-dimensional. So we've got one dimension for your radius, another dimension for your radius because we squared it, and then a final dimension for your change in x. Gives us 3 dimensions or volume. Okay, so that gives us volume, not right in purple, volume is equal to the integral from -2 to 2 of 1/2 pi is a constant, so I'm going to pull that out, pi over 2, times our radius squared, 4 minus x squared over 2 squared in terms of x. Okay, if I want to simplify this again, I'll have, when I square this, I'll get let's probably just square this all together. Yeah, let's do that. What happens when I square 4 minus x squared? What happens when I square 4 minus x squared?
You what?
16
Square it?
Yep.
minus
Okay, 16.
4 x to the fourth.
It's the fourth power and minus
8.
8x squared. Okay. And then on bottom I'll have 2 squared is 4. Okay, so I'm going to pull out that 4 since that's still a constant, and that'll give me 1
So
over.
pi.
Well, that 4 is on the bottom of a fraction, so this is really 1/4 times pi over 2 is
Oh,
pi over 8. Times the integral from -2 to 2 of x to the 4th power minus 8x squared plus 16 in terms of x. And then we can integrate normally. Okay, any questions on our math so far? We've got a little bit of geometry in our setup for the semicircle. We've done the algebra so far, so last part, easiest part, we've got our calculus. I'm going to multiply pi eighths times our integration with power rule. So this is x to the 5th over 5 minus 8 x cubed over 3 plus 16x from -2 to 2. Okay, so plugging in our upper bounds, I'll have 2 to the 5th power, or 32, minus 2 to the 3rd power, so that's 8 by 8 is 64, plus 16 by 2 is 32, minus my lower bound. -2 to the 5th power is -32. -2 cubed is -8 times the -8 I've got on the outside would give me a positive 64 over 3. And the -2 times the 16 would give me a -32. So once again, all of our signs are opposite, which is going to happen anytime you've got a shape that is symmetric around the y-axis. So because our start point was the same distance away from 0 as our endpoint, this just worked out this way. But 32 over 5 plus 32 over 5 is 64 over 5. -64 thirds minus 64 thirds is -128 thirds. And 32 plus 32 is 64. Okay, so we should be able to add all of this together and get our final answer. Nothing reduces, unfortunately, but I'll do my best really quick by hand, and we'll check and make sure I've got this right. So I'm going to go to 15, I think. So this will be, I'm leaving this in 64th, since everything is already in terms of 64. This is 64 times 1, 64 times 2, 64 times 1. I think that'll make our math a little bit easier. To get a common denominator, it would have to be over 15. So that would give me 3 times 64 over 15. Minus This is already 2 times 64, and I'd have to multiply it by 5. So that's 5 times 2 times 64. I had to multiply this fraction times 5 in order to get over 15. And then the 128 was 2 times 64. I'm doing that so that everything is in terms of 64ths. Plus 64 over 1, I have to multiply by 15. So that's 15 64s over 15. Okay, any questions on what I did there? Okay, so then 3 times...
Why do we need to multiply 15 on the top again?
I'm trying to get a common denominator so that I can add all of these fractions together. So since I've got a 5 and a 3, my common denominator would be 15. So I'm going to turn all of these terms into fractions over 15 so that I can add them together.
So is it like if it's only a constant on the last part, we need to multiply the least common multiple instead of like the first fraction is having like 3 and the second fraction is having like 5?
Right, so our least common multiple of really 3, 5, and 1, because if it's just a constant, it's not a fraction, we can always put it over 1, right? So least common multiple of 3, 5, and 1 is 15. In order to get to 15, I would have to multiply this 5 by 3, but whatever I do to the top, I have to do to the bottom. Same thing here.
Okay.
So for this fraction, I'd have to multiply both sides by 5, and for this one, I'd have to multiply both sides by 15. So that leaves me with 3 times something minus 10 times something plus 15 times something, which will make our math really easy, I hope. So that's 3 minus 10 plus 15. Or the negative 10 plus 15 is 5, plus the 3 is 8. So I've got 8 times 64 over 15. 3 of something minus 10 of something is negative 7 something, plus 15 something is 8 something. Okay, then my 8s will cancel. 8 and 8. To leave me with...
Why is there 8 again?
Why is there an 8 again? This 8 you mean? Or...
Yes.
Okay. So I'm going to pretend this 64 is a variable. Right over this. So we're going to say 64 is x. Then I'd have 3x minus 10x is negative 7x, right? Plus 15x would give me 8x. And since all of my variables, all of my x's are 64s,
Okay. Why did it become...
okay, that leaves me with 8 of 64s, right? Okay, now 8 and 8 can cancel, and that leaves me with 64 pi over 15 as my final answer. Is this an easier way than multiplying all of this to simplify in my head? So you don't have to do that the same way that I did. I'd be perfectly fine if you took, right after this integration step, you just plugged all of this in a calculator and got a decimal answer. That's fine too. But if you have to do this by hand, I think that's the easiest way to do it. Okay. Any questions on anything from this one? All right. Double check our answers really quick. 64 pi 15ths looks good. We had one from way earlier. Okay. I'm going to go ahead and post our examples over to the WeChat so that you'll have these to study from. And then you guys have 10 problems for homework. All right. Thank you very much. Right. So these will be due. This will be your Tuesday at midnight. For these 10 problems.
Okay.
All right. I hope you guys have a great weekend, and I'll see you on Tuesday next week.
You too.
Thank
Bye.
you.
Goodbye.
Oh wait, is the homework due on?
Oh. Sorry, Kyle. Sorry, Kyle. Cut you off. Sorry, Kyle. Cut you off. Rejoining. Okay, sorry, Kyle. What's your question? Oh, not working. What's your question? Oh, not working apparently. I can't rejoin apparently. Having issues rejoining. Having issues rejoining. What was your question?